In this video, we're going to go through what the highest wavelength necessary is for an electron to be emitted from a metal surface. And so for that, we're going to be looking at titanium, which has a work function of 4.33 electron volts. And so an electron volt can be converted into joules using the conversion factor, where 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. And so to convert the work function from electron volts into joules, all we have to do is take 4.33 electron volts, multiply that by 1.602 times 10 to the negative 19 joules over 1 electron volt. The electron volts cancel out, and so what we get is a value of 6.94 times 10 to the negative 19 joules. Now that we're in joules, we can easily work with that to be able to calculate what the appropriate wavelength will be to emit an electron from the titanium surface. So to be able to then calculate the appropriate wavelength, we can use the equation where the energy, which we just calculated, is equal to hc over lambda. And so if we rearrange that equation, what we then have is that lambda is equal to hc over E, where h is Planck's constant, c is the speed of light, and energy is the energy that we previously determined from the work function. So if we now multiply 6.626 times 10 to the negative 34 joules seconds, which is Planck's constant, with the speed of light, which is 3 times 10 to the 8th meters per second, over 6.94 times 10 to the negative 19, what we can then do is cancel out the joules and seconds, and we will get our wavelength, which is 2.86 times 10 to the negative 7 meters. Or if we were to convert that into a more standard sounding wavelength for light, it would be 286 nanometers, which falls within the UV range.